this is the last cluster for the 7th grade on statistics and probability. If we take a look at all the different topics that we have to cover, it's quite lengthy. So I just want to let you know that there is not, outside of the regular project discussion board, the homework for this lesson is the only one that you'll have attached with it for this week outside of watching the lesson videos. So be patient with yourself as you go through these. Feel free to always ask questions if you need to. So let's get going. The more random a sample, the more likely it is to give an accurate depiction of the entire population. There are multiple strategies to acquire a random sample while avoiding biases. Ms. Poor is going to plan a unit based on student interest. Without surveying every student, what are some ways that she could generate a random sample? One way would be called a systematic random sample, such as every 5th student, or every 3rd student, or every 10th student. We could also do a stratified random sample, such as splitting students into groups, such as 6th, 7th, or 8th graders, boys and girls. You could split them up by their heights or their shoe size as an example. Then a certain number of students is randomly selected from each of those stratified groups. We need to avoid biases of convenience. Those would be convenience samples, such as selecting the first 5 students who enter the class. Yes, this is easy and simple, but is an accurate depiction of all the students in the class. Or a voluntary sample, such as who wants to participate in the survey. This is easy and does avoid conflict, but is an inaccurate representation of everybody. The school board needs feedback from your parents about parent-teacher conferences this year. Help the school board out by devising a random sampling strategy and explain how to avoid biases. The school board should randomly select 50 students from the student body and mail a survey home to those addresses. This avoids the bias of convenience, where they may only survey parents who come to conferences. Further, if each school board follows up with each mailing, then it also eliminates the voluntary bias of getting data from those who choose to participate. Inferences can be made about a large population by discovering characteristics of smaller representative sample. We can make inferences about a population using data from representative samples and proportional reasoning. Paige has scored the following point totals in the first fourth of the season. The school's single season record was set by someone who scored 166 points in her first 11 games. Is Paige going to break that record? Provide an example with reasoning. So far, her total points is 77, so I added 14 plus 5 plus 17 plus 15 plus 26. This represents a fourth of her season. So therefore, each fourth, we're going to assume that she does 77 points each fourth of the season. So 4 times 77 would say that she would score 308 points through the season. Let's say there's a 20-game total. So the single season record was held by someone who did 166 points in her first 11 games. So on average, that student completed 15.1 points per game. So if I multiply that by 20 games, that would be 302 points. This assumes that particular girl maintained her average throughout the remaining of the season. So therefore, Paige is certainly on her way to breaking the record because she is we assume if she stays on the same path that she will get 308 points. Paige's next 2 games are shown below for games 6 and 7. If the actual season scoring record is 299 points, is Paige still on pace to break? Explain using the new data. Well, Paige's new average would be 77 plus 11 plus 14, so 102 points over the 7-game stretch. That says that she makes 14.6 points per game on average, or the mean. So if we were to take 14.6 times 20 games, that would give her 292 points for the season, assuming she has the same average throughout. This new data brings her mean points per game down, and since 292 is less than 299, she is not on track to break the single season scoring record. How many home runs will be hit in a 15-year career? We have the 6 seasons listed and home runs listed below. So the total home runs, if we add them all together, is 121. Breaking that down per season, it is 20.2 mean home runs each season. Multiplying that by 15 seasons, there would be, assuming the home runs stayed the same, 303 home runs in a 15-year career, assuming that each season, this particular baseball person's mean stays around the same. Mrs. Romero's class competed with Mr. Nelson's class in a discount card fundraiser. Individual sales are below. Whose class had the best participation? We can use the mean and the mean absolute deviation to make comparisons between these two populations. Let's use the mean and mean absolute deviation to support our opinion. So the mean for them, again, is to add them all up and divide them by how many there are. So the mean for Mrs. Romero's class is 4.9. And the mean for Mr. Nelson's class is 4 1/10. The student who sold 32 in Mrs. Romero's class is a drastic outlier and is affecting the mean for this class. So although it appears higher, does it really mean that it's higher? Therefore, it is best to calculate the mean absolute deviation to determine how varied each class data really is from the mean. So remember, the mean absolute deviation tells us how far away from the average the points are, so how spread out the data is. So I've calculated the mean absolute deviation, referred to previous videos to recall how to do that. And we get 3 7/10 for Mrs. Romero's class and 2 2/10 for Mr. Nelson's class. I can see that Mr. Nelson's class sold closer to the average than Miss Romero's class because the number is smaller. Therefore, we can say that Mr. Nelson's class had better participation since more students were closer to the mean. Processing data both visually and numerically allows for more accurate comparisons between two populations. We can also use the mean and interquartile range to make comparisons between two populations. The 10 fastest students in 7th and 8th grade at Dakota Middle School were asked to run the 100-meter dash. Use the median and interquartile range to explain which class is the fastest. So I first listed all of the times in order from least to greatest. And then I found that the median for the 7th grade class was in between 14.6 and 14.8, so that would be 14.7. In the middle between 14 and 9/10 and 15 and 2/10, we'd add them together and divide by 2, such that it would be 15 and 5/100. To find the interquartile range, recall that we split our data in half and find quartile 1 and quartile 3, and then find the difference between them. So 15 and 9/10 minus 13 and 7/10 is 2.2, and 15.6 minus 13.8 is 1.8. Sometimes it's best to look at pictures to help us identify and compare between populations. So this top one must be the 8th grade team, because if we look at the smallest number is 12.7, matches here, and the highest number is 15.9, which matches here. So this top one recalls the 8th grade team, and the bottom one recalls the 7th grade team. Although the 8th grade had the fastest runner, and the 7th grade had the slowest time, 7th grade as a whole performed better since most of the data points are more evenly distributed. Use them, okay, there are 2 boxes, each with 100 bills of value varying between $1 and $50. Susan is allowed to pull a sample of 20 bills from each box, but then must choose one box to keep. Use the mean, MAD, median, and IQR to help Susan select a box. Create a dot plot or box plot to provide a visual that supports your opinions. So I have our boxes laid out. The mean or the average of each box from the bills that I pulled out were 10.15 and 10.1. Very similar. So let's move on to the MAD. The MAD for each one is 9.94 and 5.94. I can tell that in box 2, the numbers are closer to the average, the ones that I chose. And in box 1, they are more spread apart. The median is 5 and the median is 7 and 5/10. So the median is larger in box 2. The interquartile range is 9 and 15. Let's take a look at the box plots, or excuse me, the dot plot for each one. Notice that the box 1, most of our data is piled up on the lower end, less than $10 range. Whereas the right-hand box 2, the majority of them is between $5 and $20. And since the mean is higher and from the dot plot, the bills are more consistently higher, I would recommend box 2. A third box is brought in for Susan to consider. Should we keep box 2 or should we select box 3? So I brought over our data, the mean, MAD, median, and IQR of box 2. Box 3, the mean is 9.85, slightly smaller than the mean of box 2. The MAD is slightly higher, so the data points are more spread out from the mean. The median is 10, and yes, that is higher, can't really tell from here. And further, the IQR is more spread out since the range between the first and the third quartiles is 19, which is higher than the interquartile range of box 2. Because the mean is higher and its MAD and IQR are lower with box 2, we should recommend box 2 still. Box 3 is simply too variant and provides a riskier opportunity. Let's perform 10 spins with each spinner, then record our results as 10 trials and then summarize them in the frequency tables. Subtract the number of sectors so that it looks similar to mine. And we want to do, we're going to spin it 10 times. So I can click spin, and the first one is blue. So I'm going to put B for blue. And then I'm going to spin again. And the second one was gray. Notice it's keeping track for us over here. And we ended up with gray again. It looks like they counted that as gray. And gray. Gray's kind of winning out here. Another gray. Oh, we got a blue. Funny, we haven't got a pink yet. Another gray. A blue. And a pink. Oops. And a pink is what we ended up with. Pink. Okay. So of the colors, I'm just going to move this over a little bit so that we can see. Of the colors, we had blue, pink, and gray. The frequency in which we got blue was 3. The frequency in which we got pink was 1, and gray was 6. Let's see what would happen if we altered this a little bit so that it matches our new different one here. On the second one here, notice that I've changed these little percentages a little bit so that it can mimic the one in our presentation here. So I'm going to keep track over on the right even though you won't be able to see it because of the screen here, but you'll be able to see the count all together on our video screen. So let's start with our first spin and see how it's different. So we got pink first. Then we got blue. Another blue. Pink. A pink. Blue. A lot of pink and blues here. Pink. And blue, not a single gray. Goodness. So our tally chart says that of the blue ones, we got 5. Of the pink ones of our trial, we got 5. And then of the gray, we got 0. All right, let's bring it back to our presentation. Just a couple of quick remarks here about the different, these two pieces here. Notice that there are equal amounts of pink, blue, and gray, and here it was offset a little bit. Since all the outcomes are the same, we would call this a fair spinner, or this would be an unfair spinner since they don't all have the same outcome or possible outcome as the rest. So going to the next room here, write the probabilities based on your experiment with the two spinners. So the first one here, we ended up with 3 out of 10 happening to be blue, or 30%. Okay, or pink, I'm sorry, 1 out of 10. So 10%. The blue, therefore, was the 3 out of the 10. And that gave us 30%. And then the gray was 6 out of 10, or 60%. Okay. The pink and what I would say the unfair was 5 out of 10, which gave us 50%. And the blue also gave us 5 out of 10, or 50%. And then we had 0% for gray, because we had 0 out of 10. Now, what we should have expected was, because this is equally split into thirds, that we should have gotten 33 1/3% for each one of these. Each one should have been 33 1/3%. Here I set my pink to be 66.6%. I set my blue to be 25%. And I set my gray to be 8 1/3%. Okay, altogether it should have been 100%. Now when I compare my pieces to each other here, I can see that the only one that kind of came close in our experiment was the blue. Otherwise, the pink and the gray were way offset from each other. In the unfair one, we should have seen more pink percentages, but it looks like pink and blue were nearly the same, or they are nearly the same. They should have been a little more spaced out in their percentages. And gray should have happened the least amount, still a little, I should have at least come up one time, but such is luck here. Jesse tested a spinner and recorded how many times each color occurred in the frequency table below. Find the experimental probability of each color. So it looks like we have a total times that he had spun the spinner was 7 plus 3, which is 10, plus 2, which is 12. So the orange turned out to be 7 out of 12, and the yellow turned out to be 3 out of 12, or 1/4, and the green ends up 2 out of 12, or 1/6. Now when I try to decide which spinner it is, look, this one's equally distributed into thirds. And these aren't 1/3 or even close to. Notice that when I compare all of the probabilities here, the orange came up the most and the yellow and the green came up about the same. So I would say that Jesse probably was using spinner B for his experiment. We know that the theoretical probability of an event is the ratio of favorable outcomes to all possible outcomes. There are 7 cherry, 3 lemon, 6 lime, and 4 orange juicy splash fruit chews in a bag. If we pull out a fruit chew at random, what is the probability that we will get a lemon or a lime fruit chew? So let's identify the probability of getting the cherry, the orange, the lemon, and the lime. Total possible outcomes we have are 20 when I add all of the different flavors together. So a cherry would be 7 out of 20, or 35%. Achieving a lemon would be 3 out of 20, or 15%. The orange is 4 out of 20, or 20%. And the lime is 6 out of 20, or 30%. We're curious about a lemon or a lime. So I will take the probability of lemon and add it to the probability of lime. So 3/20 plus 6/20 gives us 9/20, or 45%. What is the probability we will not get a cherry? So we want to know the probability of not cherry. So that would be the probability of a lemon or lime or orange. So then I can add their probabilities together. Lemon is 3/20 plus lime is 6/20 plus orange is 4/20, for a total of 13/20, or 65%. Similarly, we can see that getting a cherry, as listed above, is 35%, or 7 out of 20. Notice that the probability of a cherry plus the probability of not getting a cherry is equal to 100%. These are what we call complementary events. Complementary events add up to one whole, or 100%. Let's take a look at our bag of marbles here. Let's identify the probability of obtaining a purple, not purple, and I have another way to show you about obtaining a not purple, and then a purple or a green. So it looks like together I have 5 different marbles. So 3 of the 5, or 60%, are purple. Those that are not purple then are 1 minus that of being purple, which is 5/5 minus 3/5, which is 2/5. Or we could use percentages. 100% minus those that are purple gives us those that are not purple, so 40%. Purple or green. 3/5 are purple, plus 1/5 which are green, so a total of 4/5, which equals 60% plus 20% equals 80%. So 1/5 is the 20%. We can add the theoretical probabilities of 2 events to find the probability that one event or the other will happen. The probabilities of complementary events add up to 1. Theoretical probability of an event is the ratio of favorable outcomes, what we want to happen, to all the different possible outcomes. In a bag with 3 pink marbles, 1 white marble, and 4 green marbles, let's find the probability of not pulling a white. Altogether, it looks like I have 8 marbles. So the probability of getting a pink is 3/8, probability of getting a green is 4/8, and the probability of getting a white is 1/8. We want to know what the probability of getting not white is. So not white would be pink or green. So 3/8 plus 4/8 is 7/8, or 87.5%. When spinning this spinner, what is the probability of getting a 2 or a 6? The probability of 2 is 1 out of 9. The probability of getting a 6 is 1 out of 9. So the probability of 2 or 6 is 1/9 plus 1/9 equals 2/9, or 22.2%. Select the answers that represent complementary events for the spinner above. The probability of getting a 1 and the probability of not getting a 1. So we know that the probability of getting any number is 1 out of 9. So the probability of getting a 1 is 1/9, and the probability of not 1 would be 1, 2, 3, 4, 5, 6, 7, 8/9. Since they both add up to a 100%, this is complementary events. The probability of getting a 6 and the probability of not getting a 6. So the probability of getting a 6 is 1 out of 9. The probability of not getting a 6 is 1, 2, 3, 4, 5, 6, 7, 8/9. Since 1/9 and 8/9 gives me 100%, these two are complementary events. The probability of getting a 1, 2, or 3, and the probability of getting 4, 5, or 6. The probability of getting a 1, 2, or 3 is 3/9. The probability of getting 4, 5, or 6 is also 3/9. This is not a complementary event because we do not add up to 100%. 3/9 plus 3/9 is only 6/9. The probability of getting an even and the probability of not getting an even. The probability of evens is 1, 2, 3, 4/9. And the probability of getting a not even is 1, 2, 3, 4, 5/9. Since the probabilities add up to 100, these two make up a complementary event. On a standard six-sided number cube, find the probability of not getting a 3. So the probability of not getting a 3 would be 1, 2, 4, 5, or 6. So 5, 6. Or 1 minus the probability of getting a 3, which would be 1 minus 1/6. So 6/6 minus 1/6 is 5/6. Roll a 2 and win a prize. Brooke wants to be sure she has enough prizes for 60 to 90 players. The probability of getting a 2 rolling a dice is 1/6. The total observations is between 60 and 90 players. So I'm going to create a table here. We expect that 1 out of 6 times we will get a 2. We need to multiply that times the minimum number of plays, which is 60. Well, 6 times 10 is 60. So 1 times 10 is 10. The maximum number of plays is 90, and 6 times 15 gives us 90. So 1 times 15 is 15. Theoretically, Brooke will need between 10 and 15 prizes if there were between 60 and 90 observations. Pick a pink marble and win a prize. The total number of observations is 80. The probability of getting a pink is 2 out of 5. So 2/5 equals how many out of 80? Since 80 is our observations or the number of trials. Well, since 5 times 16 is 80, 2 times 16 is 32. This particular game, we would expect to need 32 prizes. We know that the theoretical probability of an event is the ratio of favorable outcomes to all the possible outcomes. So the lead pencil company has a 15% defective rate. So this means that the probability of obtaining a defective pencil is 15%. So if we had 75 defective pencils in our last shipment, how many pencils were in the whole shipment? We can write a proportion here. So 15 out of every 100 are defective. We'll set that equal to 75 were defective. So notice that I have defective in the numerator and total pencils in the denominator. So we want to know how many were in the total shipment. Well, I know that 15 times 5 is 75. So therefore, if I took 100 times 5, I would end up with 500. So therefore, there are 500 pencils in the shipment. We can use theoretical probability, the total number of observations, and proportional reasoning to predict the number of times that an event will occur. So Zeus is running a game booth in which players win a prize. if they draw a silver marble from a bag that contains 2 white marbles, 1 silver marble, 2 black marbles, and 3 red marbles. Zeus is expecting the game to be played 40 times. How many winners can Zeus expect? Well, we know that 1 out of 8 of the marbles would be the winning probability. If we set that to what over 40, how many times can we expect there to be winners? So 8 times 5 is 40, so 1 times 5. So we can expect Zeus to have 5 winners. If we spin the spinner 40 times, how many times can we expect the spinner to land on D? Well, the spinner should land on D 1 out of every 4 times, but we are spinning 40 times. So 4 times 10 is 40, so 1 times 10 is 10. We can expect it to land on D 10 times. Will this always happen? No, but this is the expected value. When rolling a standard 6-sided number cube, predict the number of times a 1 will be rolled if you roll 24 times. So a 1 comes up 1 out of 6 times on a 6-sided cube, and we are rolling 24 times. So 6 times 4 is 24. So we would expect 1 times 4, we would expect to roll a 1 4 times. When rolling a standard 6-sided number cube, predict the number of times you will roll at least a 3. So if we roll at least a 3, that concludes that we'd have a 3, a 4, a 5, or a 6. So 4 out of 6 would be the probability of rolling at least a 3. But we're rolling 60 times. So 6 times 10 is 60, so 4 times 10 would be 40. So we can expect to roll a 3, a 4, or a 5, or 6 40 times. The accuracy of experimental results improve when we increase the number of observations in an experiment. Ashley says, pull a tile, look at it, and put it back in the box. You can do that 20 times. Then guess which 9 tiles are in the box. Paul says, I better write these down. So here are Paul's results. So we have color tiles, purple, black, blue, and pink. We tallied and we have a frequency. So the purple ended up being 6 out of 20 times, black 3 out of 20 times, blue 3 out of 20 times, and 8 out of 20 times. So 40%, 15%, 15%, and 30% respectively. If there were only 9 tiles in the box instead of, we can use these percentages to identify how many purple, black, and blue, and pink there should be. So we'll take each percentage and multiply it by the 9 tiles. So we could expect there to be about 2.7 purple, 1.35 black and blue, and 3.6 pink. However, we can't have a portion of a tile, so we'll want to round. So we could say that we think that there are 3 purple, 1 black, 1 blue, and 4 pink. So if I add them all together, we certainly do have the 9 tiles. But the actual tiles are 3 purple, 1 black, 2 blue, and 3 pink. But that's okay. We were very close based on the experimental results that we had. The accuracy, we know, improves with the number of observations that we are experimenting with. So let's look at one of these grabbing games. Let's say we kept track and that there were 204 prizes won when it was played 1,700 times. So that means that we won a prize 204 times out of 1,700, or 12% of the time we won a prize. But let's say it's the busy season and the game is expected to be played 800 times. How many prizes can we expect to be seen? Well, we can take 800 times 12%, and we could expect to give out 96 prizes. The lead pencil company, there are 8,400 pencils in the whole shipment. Mr. Boyd had 59 out of 400 pencils that were defective. Can we determine how many defective pencils were in the whole shipment? So if we had 59 out of 400, that gives us roughly 14.7%, or about 15% when rounded. So if we were to take the defective rate times the number of pencils that we have, we could estimate that there would be 1,260 defective pencils in the shipment. Miss Romero shows her class a bag containing 12 coins and agrees to draw 1 coin at a time. Show the class and put it back in the bag. The table on the left shows the first 12 observations. The table on the right shows all of the observations the class had done. Which set of data is more likely to help the class guess the amount of money in the bag? Calculate the experimental probabilities for both tables and use them to estimate how much money is in the bag. So on the left, we show the first 12 observations. So there were 3 out of 12 nickels, 3 out of 12 pennies, 3 out of 12 quarters, and 3 out of 12 dimes. Turning them into percentage, we say that there are 25%. So if we had 12 coins times 25%, we would end up with 3 nickels, 3 pennies, 3 quarters, and 3 dimes, the exact same results that we observed, since there wasn't any variety in our numbers. So if we were to take 3 times 5 cents, we'd get 15 cents. 3 times 3 cents is 3 cents. 3 times 25 cents is 75 cents. And 3 times 10 cents is, 3 times 10 cents. So adding all of them up, we get $1.23. So now let's look at the results if we did on the right-hand side. So we did more pulls from our bag to see what happens. So we have 80 observations. So 6 of the 80, or 8%, were nickels. 13 out of 80, or 16%, were pennies. 34 out of 80, or 43%, were quarters. And 27 out of 80, or 34%, were dimes. So, but we only have 12 coins, so we will multiply each percentage by the only 12 coins in which we have. So 8% of 12 would be 96, 16% of 12 is 1.92, 43% of 12 is 5.16, and 34% of 12 is 4.08. But again, we can't have a portion of a coin, so we'll round them to 1 nickel, 2 pennies, 5 quarters, and 4 dimes. So if I count across, I've got, let's see here, 3, 8, 12 coins all together. And then multiplying them by their respective denomination, we have 5 cents plus 2 cents plus $1.25 plus 40 cents, so $1.72, which is the correct answer. So notice that based on more observations here, we're increasing the accuracy of our estimate by increasing the number of our observations. Possible outcomes for compound events can be listed and counted. Let's use tree diagrams to find the sample space of independent and dependent events. Let's say we need 1 pencil and 1 pen in our pencil case. We have 2 orange pencils, 3 pink, and 2 green pens, and 1 blue pen. What are all the possible outcomes for choosing 1 pencil and 1 pen? So for our pencil choices, we have 3 pink ones and 2 orange ones. Once we pick our pencil, then we have our pen choices. We have 3 pens. We either have 2 green or 1 blue. So for each one we choose, we have 2 green or 1 blue. I see that I have 5 choices for my pencils, 3 choices for my pens. We could multiply them together or count that there are 15 outcomes. Independent events, where one event occurring does not affect another event. So just because I chose a pencil does not depend on what my pen choice would be. So pencil choice does not affect our pen choice. So therefore, these are independent events. We could similarly see that if we chose our pen first and then our pencil, we would still end up with 15 outcomes. This is known as the counting principle. So if there are m ways to do one thing and n ways to do another, then there are m times n ways to do them both. In a variety pack of erasers, there are 1 pink, 1 green, and 2 yellow. Fatima needs 3 erasers in her pencil case. What are all the possible ways she can choose 3 of them? So if we had our first eraser choice, we could have a pink, a green, or 2 different yellows. Then, depending upon what we chose for our first one, our second choice is slightly different. If I chose a pink, I only have a green or 2 yellows to choose from. If I choose a green first, my only options are pink, then yellow or yellow, and so forth. If I choose a third choice, my choices get limited because I'm taking away from what I already had to begin with. These are known as dependent events. One event occurring affects another event. So our first choice affects our second choice because I may not have one of that color left in this particular situation. So we can call this, I had 4 choices for my first event. I took one away, so now I only have 3 choices. And for my third choice, I took another away, so I only have 2 choices. So altogether, I have 24 outcomes. Allie has exactly 4 pairs of socks mixed up in her drawer. They are green, blue, orange, and yellow. If she pulls out 2 socks, what are all the possible different outcomes? And are these independent or dependent? So our first sock, we have 2 green plus 2 blue plus 2 orange plus 2 yellow. So we have 8 choices. Our second, if we took away a sock, now I only have 7 choices in my drawer. So I have 8 socks times 7 socks, so 56 total different outcomes. These are dependent because my first sock choice definitely affects my option for my second choice because I don't have an additional sock in there. Tree diagrams and the counting principle can be used to determine the sample space of more than one independent or dependent event. Let's use a tree diagram to find the sample space of independent and dependent events. Determine the number of possible outcomes for each set of compound events, then order them from least to greatest number of outcomes, pulling 2 marbles out of bag of 10 without replacing the first marble before pulling out the second. So because these are dependent events, I have 10 marbles that I started with, and then because I didn't put it back, now I only have 9 marbles for my second choice, so a total of 90 choices altogether. Drawing 2 cards out of the deck of 52 without replacing the first card before drawing the second. So I have 52 cards to start with, but then when I take one out, I only now have 51 cards. So total, I have 2,652 options that I would have. Drawing 2 tickets out of a bowl of 20 tickets without replacing the first ticket. So I started with 20 tickets. I took one out and I only have 19 left. So I have 380 options. Notice that the word without replacement is key here. These are all dependent events simply because without replacing, one choice affects the second choice. Take a moment to pause the video and determine if each set of events is independent or dependent. Flipping 3 coins is independent, doesn't affect the second one. Pulling 2 marbles without replacement. Without replacement is our key that it is dependent. Pulling 2 marbles while replacing. This is independent. We have the same amount of marbles the first time as the second time. Drawing 2 cards from a deck at the same time. This is also dependent. Whether it's the same time or one at a time, we're still having the same amount of cards. Rolling 2 number cubes. Independent. Rolling 1 number cube does not affect the outcome of rolling a second number cube. Spinning 2 spinners that each have 4 equal sections. Again, independent. The one spinner does not affect the second spinner. Once we know how to find the total number of outcomes for compound events, we can calculate the compound probabilities with independent or dependent events. So let's say we have the following tickets, a green, an orange, and a purple. One ticket is pulled out of the box at random. The ticket is not put back in the box. What is the probability of pulling 1 green and then 1 orange? So this would be considered a dependent event because one is affected over the other. So we have these 3 tickets and we're not putting it back in the box. So if I pull a green, my only options then are orange or purple. If I pull the orange, my only options are green and purple. And if I pull a purple, my only option is green or orange. So the probability of getting a green ticket is 1 out of 3. So then I'm going to be focusing just on these first set because these are no longer valid. The probability then of getting an orange ticket after I pull the green ticket is 1 out of 2. So multiplying them together, 1/3 times 1/2 is 1 out of 6. One ticket is pulled out of the box at random, the color is recorded, and the ticket is put back in the box. So these would be considered independent events. What is the probability of pulling 1 green and then 1 orange? So if I put the green ticket back in the box, That means that I have all three to choose from for my second option. So still the probability of getting a green ticket is 1/3. We're still looking at that first set of options, and the probability of getting an orange ticket is also 1/3. So 1/3 times 1/3 is 1/9. At the end of the month, one ticket is pulled and it is not put back in the drawing. Then another ticket is pulled. What is the probability that May will win 2 certificates? So May has 4 tickets, Ashley has 2, Jack has 3, and Diego has 4. So May winning the first pull would be 4 out of 13. Let's say these pink ones are May's. There are 2, 4, 6, 8, 2, 8, 10, 12, 13 tickets. So she has 4 chances to get the first 4 out of 13. Then that ticket is no longer valid because we already pulled it out and we're not putting it back in. So these are dependent events. So May then has the possibility of winning 3. She has 3 tickets left since her first one was already taken away. Now we have 12 options left. So 4/13 times 3/12 is equal to 12 156. If I divide the top and the bottom by 12, we get 1 out of 13. Fill in the blank. In a jar, there are 5 quarters, 3 dimes, 2 nickels, and 1 penny. 1 coin is randomly subtracted from the jar and put in a wallet, so therefore it is not replaced. Then another coin is selected. Since it is not replaced, these are dependent events. The total number of outcomes is 110. Because our first choice is 11 options, then I'll only have 10 options left when I take one out and keep it. So 11 times 10 is 110. The probability of selecting a quarter and then a dime. So if I select a quarter, I have 5 out of 11 chances to get a quarter. I then have, let's say I did pull a quarter, I still have 3 dimes left in the jar, but now I only have 10 to choose from. So 5/11 times 3/10 is 15/10, which is equal to, when I divide them both by 5, 3/22. There are 3 pinball machines, 5 video games, and 2 racing games. What is the probability that each student will choose a video game or a pinball machine? So if there are 3 pinballs, let's represent that by P times, or PPP, and racing is RR, and 5 video games, so VVVV. So the probability of choosing the pinball is 3 out of 10 since there are 10 total options. The probability of getting racing is 2 out of 10, and the probability of a video game is 5 out of 10. We're particularly interested if each student chooses, both of them choosing a video game. So the probability of choosing a video game first is 5 out of 10, times the probability of choosing a video game the second is still 5 out of 10 because one does not affect the other. These are independent events. So 25/100. Further, if they both choose the pinball machine, we would have the probability of choosing the pinball machine times the probability of the second student choosing the pinball machine. So 3/10 times 3/10 is 9/100. But because we have the word or, a video game or a pinball machine, we need to find that either of these events will occur. So both video or both pinball means we need to add their probabilities together. So 25/100 plus 9/100 is 34/100, or 34%. Let's keep the same thing, except what is the probability that at least one of them will choose the pinball machine? So at least one pinball would mean that somewhere in our probability we would need to assign at least one pinball. So pinball and pinball, video and pinball, pinball and video, racing and pinball, or pinball and racing. These are still independent events. So we know from the previous slide that pinball and pinball is 9 out of 100. Video in pinball would be 5/10 times 3/10, so 15/100. That is the same probability as pinball and video, so 3/10 times 5/10 is 15/100. Racing and pinball, 2/10 times 3/10 is 6/100. And pinball and racing again is the same, just reversed. So now that we have all of our different options, we need to add them all together. So the probability of at least one pinball is 9/100 plus 15/100 plus 15/100 plus, oh, I think I have one too many. I got a little excited there apparently. Ooh, oh boy. Okay, so 9/100 plus 15/100 plus 15/100 plus 6/100 plus 6/100 is 51/100. Again, keeping the same scenario. This time we want, what is the probability that less than one of them will choose the video game? So less than one of them will choose the video game. All right, so less than one video game would be pinball and pinball, racing and racing, racing and pinball, or pinball and racing. Notice there is no video game listed in that probability. So this is the same as finding the probability with no video games. So the probability of getting pinball and pinball we know is 9/100. Racing and racing, 2/10 times 2/10, which is 4/100. Racing in pinball, 6/100. And pinball and racing is also 6/100. So we add them together. 9/100 plus 4/100 plus 6/100 plus 6/100 is 25/100 or 25% probability that they will choose no video games. In the box, there are 5 caramel, 3 nut-filled, and 2 fruit-filled chocolates. What is the probability that these students will both choose 2 nut-filled or 2 fruit-filled? So we need a nut and nut choice. So the first chooses a nut and the second chooses a nut. Since we're taking up from the box of chocolates, once a chocolate is gone, we can't put it back because you're going to eat it, right? So you're not putting a bite back in the box. So these are dependent events. So there are 3 out of 10 which are nut filled. And if I choose a nut filled for my first option, I only have 9 left to choose for my second. And further, there are only 2 options left because I took one of them from my first option. So 3/10 times 2/9 is 6/90. Now we need the fruit and fruit. So if the first student chooses fruit, there are 2 out of 10 which are fruit. And if the second also chooses fruit, one of the fruit's already gone, so I only have 1 out of 9 chocolates left to choose from, which are fruit. So 2/90. Again, we add them together. So 2/90 plus 6/90 is 8/90 or 8.9%. Let's keep the same scenario going, except this time we want the probability of choosing at least one fruit. But we're only choosing 2, but we need at least one fruit. So that would be, we would have the option of choosing fruit and fruit, nut and fruit, fruit and nut, caramel and fruit and caramel. So those are the options with at least one fruit. So 2/90 from the previous one for fruit and fruit. Nut and fruit would be 3/10, and then fruit would be 2/9. Fruit and nut would be 2/10, and nut would be 3/9. Notice that the second option we already have 1 less because we already took a fruit, but it depends what the first fruit was. Caramel and fruit, caramel there are 5 out of 10 options times the fruit option 2 out of 9 plus the option of fruit and caramel 2/10 times 5/9. So multiplying them together, 2/90 plus 6/90 plus 6/90 plus 10/90 plus 10/90 is 34/90. So the probability of getting greater than or 1 fruit when we choose 2 is 37.8%. Okay, keeping the same scenario, what is the probability of choosing less than 2 caramels? So this would then be the complement of choosing 2 caramels. So less than 2, the opposite of choosing less than 2 would be choosing all caramels. So what we can do is the probability of choosing less than 2 caramels is equal to 1 minus the probability of choosing a caramel and a caramel. So we don't have to write out all those pluses. It could save us some time here. Well, if I chose a caramel and then a caramel, 5 out of 10 would be caramel, times we would then have 4 left out of 9, which are caramel. So 1 minus 20/90ths, converting 1 to 90/90ths minus 20/90ths is 70/90ths, or 7/9. So the probability of choosing less than 2 caramels is 77.8%. In a bag, there are 5 blue marbles, 6 red marbles, and 1 yellow marble. 1 marble is pulled out of the bag and the color is recorded. The marble is not put back in, so these are dependent events. Another marble is pulled out and its color is recorded. What is the probability of pulling out less than 2 blue marbles? Well, pulling out less than 2 blue marbles would be the opposite or the complement of 1 minus the probability of both of them being blue. So if they both were blue, we'd have 1 minus, there's 12 marbles altogether. 5 out of 12 for the first choice, we would have 11 left and only 4 blue ones, considering we already took a blue one out. So 1 minus 20 132nds. So 132 over 132 minus 20 132nds is 112 132nds, which is 28 over 33. In the waiting room of an office, there are 7 magazines. 3 are sports, 2 are fashion, 2 are news. If 2 magazines are randomly selected, what is the probability of choosing less than 2 sports magazines? Well, then the opposite would be the complement. So 1 minus sports and sports. So 1 minus 3 out of 7 is sports. If I already take a sports magazine, there are 2 sports left and only 6 magazines to choose from. So 1 minus 6 out of 42, which is the same as 1 minus 1/7, which is the same as 7/7 minus 1/7, so 6/7. We'll pause here. The last part of statistics and probability is to use simulations to find experimental probabilities for these compound events. So let's use a coin to generate 15 trials of guessing on 2 true and false questions to find the experimental probability the student will both get them correct. So there are 3 steps when you're trying to generate your own experiment to find probabilities. Is to choose a method to model the situation and designate specific outcomes of the model to specific outcomes of the situation. Define 1 trial, and then conduct the number of trials desired and record in a frequency table. So using the example from above, we're going to use a coin to generate the true or false. So we're going to let heads represent guessing correctly and let tails represent guessing incorrectly. 1 trial is 2 flips of the coin to represent the outcome of guessing on both problems. So let's say we did this. Let's say we flipped our coins 15 times and got the following outcomes: heads, 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 tails, heads, tails, tails, heads, etc. Then we can fill in our frequency table to match the outcomes. So the number of who they got correct would be heads and heads. So I see that there were 1, 2, 3 where they got heads, heads, meaning correct, correct. And then we can count the rest for the remaining. Further, the relative frequency then is out of 15 trials, 3 out of the 15 were 0 correct, 9 out of the 15 were 1 correct, and 3 out of 15 were all correct. The theoretical probability then, theoretical meaning what should happen, is that if we got the first problem correct or incorrect, then our second problem would be correct or incorrect. So these are independent variables because one does not affect the other. So the probability or the relative frequency of getting 0 correct is 3 out of 15 or 20%. The theoretical probability is 1/4. So out of the 4 options that we have altogether, 1 out of 4 would be 0 correct, or number correct would be 0. So 25%. Since these are fairly close to one another, this is a good model that will work. Ashley saves 5/6 of the shots that are taken against her. Use a number cube to generate 10 trials that represent a shot against her. So steps for generating the frequencies. Let's choose the model. So since we're talking about 6 shots, we could use a number cube to do this. So we're going to let 1, 2, 3, 4, and 5 represent saving the shot, because that would be a 5 out of 6 probability. Then we'll let 6 represent not saving the shot. 1 trial is 1 roll of the number cube to represent the outcome of attempting to save the shot. So let's roll a number cube and see what actually happens. And it looks like up in the corner I'm able to roll. So let's roll the dice and see what we get. We got a 2. So for our 2, we saved the goal. So I'm just going to kind of keep track here. Okay, we'll go back. We'll roll again. We got a 3, so we saved. So instead now we have 2 of them. We have to do this 10 times. We have a 1, so we've saved again. So we're up to 3 under the saved goal. A 5, so we saved it again. A 4. A 5. Another 5, so far so good. A 1. Only 2 more to go here. One more. And a 3. Move our screen back in order here. So 0 times she did not save. So the relative frequency would be 10 out of 10 or 100%. Okay. We know the probability should be 5 out of 6 times, and 5 out of 6 is the same as 83%. So this was 100%, but I would still say that this is a good way to do this. You could also, again, use a spinner that had 6 options on it, letting 1, 2, 3, 4, and 5 represent saving the shot, and 6 represent not saving the shot. Although we didn't have the option of 6 coming up, remember, the more simulations you do, or the more you experiment, the closer to the theoretical probability we will get. So if we were to continue doing this, perhaps we would get a little bit closer than we already